Hello everyone, and welcome back to the series on multivariable calculus. Today we're going to be talking about a very interesting idea known as line integration, which has a variety of applications in vector calculus, complex variables, and engineering and physics. So let's start off with a brief overview of what we mean by integration. Well, usually when we talk about integrals, we're usually talking about areas bounded by curves and, say, the horizontal x-axis. So in this particular picture, we have this shaded area. Let's call it A. And this is the integral of f over some region. Right? Now, since we're going to be working in the multivariable calculus realm for this, notice that I've labeled the horizontal axis x and the vertical axis z, because technically speaking, what we have, possibly, is another axis that is going in another direction. For example, we can have this axis, for example, y, and then we have this particular surface that only has this vertical, say, paper planar region shaded in orange. So what we can think of is the horizontal axis, and I'll shade this in green. So if we traverse along that particular path, for example, we can call that C, we can say that this is the integral of f over the path C from x is equal to a to x is equal to b. Right? Now, this obviously is a very trivial extension. This doesn't really give us anything new. But what if we decide that we want to change the path C that we want to integrate over? All right? So this is what we're going to be doing now. So let's assume that u sends r to r2. So this obviously is a vector function. So let this be a vector function. And let C be the set of all points x and y such that u of t is equal to x of t, y of t for some domain of t subsetted in R. So the question that we want to answer, can we integrate f(xy) over C? So what exactly geometrically does this even mean? So let's again draw our plane. Let's assume that this is x, y, and this be z. And let's assume that we have some path in the xy plane that is here. Let's assume this is t is equal to a and t is equal to b. And then this function is going to be projected up towards some height values. For example, let's assume that this height follows that particular path. All right, so this is going to be your function f. And then we're going to have some height values. So we're going to have these little height values. And then they're going to go behind. And then it's going to follow that. Right? So it's almost like a piece of paper that is standing up on its side and then folded, right? So if we were to take this region, let's assume that this area is A, and then we were to map this to a, I guess, easier to look at picture. And again, what is this path in blue? This is going to be u of t, right? So that means this point here is u of A. And this point here is going to be u of b, and everywhere in between is u of t, where t ranges from a to b. Then what we're going to have here is u of a, u of b, and then the u of t axis. And then what we're going to have here is the heights of our particular curve located here. And then we're going to have those vertical strips giving us the area A. Right? So again, what we're looking at here is the z-axis, still vertical, but we're just parameterizing x and y with respect to u. Right, so this is just x y in disguise. Right? So this is pretty much what we're going to be looking for. So we already know how to find the area of the region located on the right. So the question is, how do we find the area on the left without directly mapping to the picture on the right? So again, we want to find the area A, which is going to be the integral along C of fxy dl, where L is the length of the path C. So L is the length of C that we traverse across, right? So that's going to be our goal and what we plan to achieve in this discussion. All right, so let's begin with a definition that's going to get us going. All right, so suppose that C is a smooth curve in R2. Now, it doesn't need to be smooth, but it needs to be at least continuous. But we're going to be assuming that it's smooth here so we can at least differentiate it in R2. Then the line integral of the function f, keep in mind f is going to be a function, along C is given by the following relation. So how would you define this particular object? So we're going to integrate along C of fxy with respect to its length. And this is going to be defined by, well, how do we define it in the typical Riemann integral case? Well, that's just going to be the limit as n goes to infinity of the sum as k goes to 1 to n of fxk yk times delta lk. So what exactly are we looking at here? Well, our particular picture is just going to be pretty much the same thing as we did in calculus, right? So what we're going to do is we're going to look at these delta L1s, for example, delta L2s. They don't have to be the same, but we would like them to be. Usually we call that a uniform partition, so that would be delta Ln. And then we're going to have vertical strips associated to each of those heights. And as we increase the number of partition points, that means the maximum of the partition magnitudes of all of those partitions will converge to 0, and then that will converge to the area under that curve. Right? So here we're going to be letting u of t be representable in terms of x of t, y of t, and if we assume that it's smooth, then that means x and y are going to be differentiable as well. So how are we going to find this particular expression? So, using the same exact methods from parametric curves, the length can be found by the integral from a to b of the square root of the derivative of x with respect to t squared, and then the derivative of y with respect to t squared dt. And this came directly from the Pythagorean theorem. But if you look very cleverly, and if I were to call this, for example, the vector a and b, and if I were to ask you, what is the norm of u? Well, you would just say, well, that's just the square root of a squared plus b squared, or something along those lines. Agreed? So that would be equal to a squared plus b squared. So if I were to take the derivative of u, what would the derivative of u be? Well, u prime of t would just be equal to x prime of t times y prime of t. And if I were to ask you what is the magnitude of u prime of t, you would just say, oh, that's the square root of a squared plus b squared, where a is x prime and b is y prime, which is exactly what we have here. Right? So this is precisely the integral from a to b of the magnitude of u prime of t dt. Right? So that's how we can find L, and then we can differentiate L if we want to. So that means the integral along C of fxy dl will be equal to the integral along C of f, let's call it, let's parameterize it. So let's say f of x of t, y of t. F of x of t, y of t. So f of x of t, y of t, and then again, let's assume that t is going to range from a to b, and then we have dl, which is the derivative of that integral, which would just be equal to the square root of dx dt squared plus dy dt squared dt. Or you can compactify this representation and just write that as the norm of u prime. So the integral of fxy dl will be equal to the integral from a to b of f of u of t, where u of t is the parametrization of all xy points along C, times the magnitude of the derivative of the parametrization function, u. And this is the primary formula for calculating line integrals. Let's do a quick calculation example just to make sure we're comfortable with working how to calculate a line integral. Let's assume that we want to integrate the function fxy is equal to xy along the path C traversed by t squared 2t, where t ranges from 0 to 1. So how would we calculate this particular line integral? So the integral along C of this function fxy dl will be equal to then the integral along our bounds of our parametrization 0 to 1. And then we're going to plug in our parametrization into our function. So x is going to be equal to t squared, y is going to be equal to 2t, and then we're going to multiply by the norm of the derivative of the parametrization. So that's going to be equal to what? So again, u of t is equal to t squared 2t. So u prime of t will be equal to 2t and 2. So it's the square root of the sum of the squares of those two components, 2t and 2. So that's going to be the square root of 2t squared plus 2 squared dt. So that's pretty much the setup of your integral. And now we just need to simplify and evaluate. So that's going to be equal to what? So that's going to be equal to the integral from 0 to 1 of 2t to the power of 3 times the square root of 4t squared plus 4 dt. Notice that there's a 4 in common with both of these terms, so we can take the square root of 4 and 2, multiply it with the 2 out front, and then factor out a 4. That's going to give us 4 times the integral from 0 to 1 of t cubed times the square root of t squared plus 1 dt. From here, now we use all our single variable calculus tricks that we learned before. For example, we can let u be equal to the square root of t squared plus 1, and then use u substitution from here. So when t belongs to the integral 0 to 1, you should be able to verify that u will range from 1 to the square root of 2. Also, u squared will be equal to t squared plus 1, and then when we differentiate this quadratic instead of the radical, which will introduce rationals, we're going to have 2u du will be equal to 2t dt, and then therefore dt will be equal to u divided by t du. Right? So once you have all this, then we can transform our integral of t into an integral of u. So it's going to be equal to 4 times the integral from 1 to the square root of 2. T is now going to look like what? So if we write this as, what's a better way to write it? Actually, currently I don't want to solve for t because that's going to be messy. So I'm going to write this as t cubed times the square root of t squared plus 1, which is going to be u squared. So that's going to be equal to u squared. dt is going to be u divided by t du. Notice that one of these u's is going to cancel out here, so that's going to cancel with that, and that's going to cancel with that. And then we're going to be left with t squared, and we know that t squared will be equal to u squared minus 1, so we can use that substitution here quite nicely. Right? So what does that look like? So it's going to be 4 times the integral from 1 to the square root of 2, and then t squared, which is the same as u squared minus 1, and the square root of u squared is going to be equal to u, and u times that u is going to be equal to u squared du. Now this is actually a very friendly integral. You can go about this in a variety of ways, but I'm just going to use the power rule because this is just going to be equal to the integral of u to the 4th minus u squared du, which we know is going to be equal to 4 times 1/5 u to the power of 5 minus 1/3 u to the power of 3. And then we're going to take the limit as u goes to the square root of 2. Take the limit as u goes to 1, and then subtract. Lots of computations you could do here, but this will come out to approximately 1.2876. But that would be the value of the line integral that we had before. Overall, the process is not that complicated. pretty much the only new part that you need to get familiar with is how to set it up. So first off, reparameterize your function of x and y in terms of t, and then do the norm of the derivative of the parameterization vector function u. And then the rest turns into a single variable calculus problem. The last thing I want to mention goes into the following question. We already know how to integrate functions over paths. In particular, these functions are scalar functions. You plug in some x, y numbers, you get a scalar, a number, back again. But can we integrate vector fields over paths also, instead of integrating scalar functions? The answer is yes. So let's go ahead and define how we integrate vector fields. So the integral of a vector field, which I'm going to represent by f, so vector field is going to be represented by f, over some path, let's call that c, dot product du, because keep in mind, f is a vector field, it's a vector, u is also going to be a vector function. So what is this object going to be? So this is going to be defined to be equal to the natural definition of it. So this is going to be the integral from a to b of f of u of t, where u is the parameterization of c, dot product with u prime of t, the derivative of the parameterization, dt. Again, keep in mind, make sure your types are correct. This is a vector, that is a vector, this is a scalar, this is a number. And that's going to give you our particular answer. Notice that there is no absolute value in this expression like there was for line integrals of functions, right? There is no absolute value. So this does take into consideration direction. So the direction will matter here in terms of how you parameterize your path. So make sure you get your direction correct. So let's actually look at a particular example. Let's consider the vector field. fxy is equal to xy and then 3y squared. So what type of function or vector field is this? So is this a conservative vector field? Is it not? So if we look at this, let's assume that it is a conservative vector field. We should be able to find potential functions if so. So that means fxy will be equal to xy, forcing our original function fxy to be equal to 1/2 x squared y plus some function of y. And then we can differentiate that with respect to y. That's going to give us 1/2 x squared plus the derivative of y, and that has to be equal to the second component, 3y squared. Notice that there's no way to cancel this 1/2 x squared term, therefore this g does not exist. Since that g does not exist, that also means this f does not exist, and therefore since the function does not have any potential functions, that means it's not conservative. It's not conservative. So it doesn't have any rotational symmetry. So what does that mean? So that means that the curl of this associated vector field f is not equal to 0. Moreover, you should be able to verify that it's equal to minus x. So it actually depends on x, and if x is at the origin, then it does have rotational symmetry. So I guess you could say it's conservative at the origin, but nowhere else. All right? So if that is the case, then what do we have? So let's find the parameterization of some path. So let's just choose our path C, because we can traverse along this path along any path, or along this vector field along any path. So let us define C such that it is parameterized by u of t equals t minus t, where t ranges from 0 to 1. Right? And you can choose a different path to traverse across this vector field if you want to do it. Right? So if that is our u, that means u prime of t will be equal to 1 minus 1. And that means our function f of u of t will be equal to, so again, what was our vector field? So this is going to be equal to x, y, 3y squared, which in the t realm is going to turn into, so x will be t, y will be minus t. So that's going to give us what? So that's going to give us minus t squared, and then 3t squared on our second term. All right? So that's going to be our f, and then we can find our line integral of our function, or our vector field. So the integral over c of the vector field f will be equal to the integral from 0 to 1, the range of our parametrization, of f of u of t, which is minus t squared, 3t squared, dot product with our derivative of our parametrization function, 1 minus 1 dt. And you should know how to find dot products by now, so you multiply the components. So minus t squared times 1, so minus t squared, and then plus 3t squared minus 1, that's going to give us minus 3t squared, and then dt. So that's going to be the integral from 0 to 1 of minus t squared minus 3t squared dt. So that's actually a nice integral, so we can integrate that from 0 to 1. What is that? Minus 4t squared dt. And then we can take the antiderivative, minus 4/3, plug in 1, 0 contributes nothing. So that's going to be equal to minus 4/3, right? Which is a negative number. So what does this exactly mean? So if we were to graph this particular vector field, what you would get is something that looks like this. So lines that go upwards above the x-axis and lines that go inwards below the x-axis, right? So what we're doing is we're traversing along the path. What was the path? Let's see if we can find it. Our path was t and then minus t. So then t and minus t. So that actually is the path here to here. So that would be this particular path. Right, so that's our particular path C. Notice that the flow lines of the vector field are going in the opposite direction compared to that of the path direction of C. That is, if we go from t is equal to 0 to t is equal to 1. So t is equal to 0 to t is equal to 1. That gives us that particular path C. Right? So since we're going against the flow of the path, if you think of it in terms of physics, we're going to be losing energy with respect to that motion. Right? So that's pretty much what this negative number represents. So what could we say? So that means on average, not necessarily always, the vector function u of t goes against the flow of the vector field F. Some people also in the physics realm define this integral as work. That is, we're losing work, or our work is negative if we're going against the flow, but if we were to go from t is equal to 1 to t is equal to 0, we will be working in the same direction as the flow. So if I were to show you a couple other pictures, so let's assume that we have some flow lines going up here, and then let's assume that you have some flow lines here, and then let's assume that we have some path. So if we have this particular path here, so for example, let's assume that this is C1, and then let's assume that this is, say, C2, and this is, for example, C3, then you should see that C1's integral kind of goes in the direction of our vector field. So you can say that the integral along C1 of f du1, let's assume that's, say, u1, will be a positive number. For C2 or for C3, you can clearly see that that's going completely against the flow. So that's going to be a negative number. So what can you say about the integral for C2? F times the derivative of u2. Will that be positive, negative, or 0? Because it appears that maybe these lines are perpendicular to the flow lines. So maybe you could say that that's equal to 0. I'll let you figure that out on your own. But these are some of the things that you definitely should know when working with line integrals of both scalar functions and vector fields. And we'll have several other applications of integrals of vector fields and scalar functions later on. Hope you enjoyed this video and see you in the next one. Take care.